Okay, so welcome to another video. We're going to solve differential equations using a different method called homogeneous method of solving differential equations. So basically, what we need to recall is that for order 1 differential equations, there's going to be 3 ways of solving them. The first way we already did, which was separable. Second one, that's going to be, ta-da, homogeneous. Third one, that's going to be exact. Okay. And one thing about homogeneous that you probably should know, and you'll definitely see in a little bit once we start doing problems, is that and that's just like a little teaser for what we're going to be doing for the homogeneous section. Okay. Now basically, in the beginning, it's going to ask us, well, how do we know that this differential equation is homogeneous? Well, that is a good question, because if we have this, for example, number 4, if we have f of xy is equal to x over y squared plus square root of x4 plus y4. Okay. Let's see. I guess we should start off with the definition of the homogeneous function. So the homogeneous function. Okay, so the homogeneous function is basically going to have any function so f of xy. So if I said that up here, you're probably like, what the heck, what does f of xy mean? Well, f of xy is just equal to a function, and basically the process we're going to be doing is that I'm going to write it down and then explain. Okay, what did I just write down? What did I just write down? Good question. So for a homogeneous function, f of x, y is equal to a function, like I said. And now if f of tx of ty is equal to t to any power, f of xy, therefore f of xy is called the homogeneous function. So basically if we get this function back, whatever degree this n is, that's going to be our, that's just going to be our degree. So essentially, if we get our function back, that's going to tell us whether it's a homogeneous function or not. And you'll see whether it's a homogeneous function or not, and then you'll see what degree it's at. Okay? So in words, so basically if you basically put the t in your function, if you put the t in your function, and then what you end up with is your function that you started off with, if you get this, then it's a homogeneous function at the degree of whatever degree you're left with. But let's just say you don't get the function that you started off with. Let's just say you get some function that has the t in it. Let's say you got, I don't know, something like that. If the t is somewhere in the function you started off with, then it's not homogeneous. Then you can't solve it homogeneously, or whatever the word is. You can't solve it using this method. However, if you do get the function back, then it is homogeneous, and you could use homogeneous to solve this differential equation. So basically it's a test case. If I get a function with t's in it, that means it's not homogeneous, which means why would I try to solve it homogeneously if I'm not going to have any luck with it, right? Okay. Makes sense? Great. Great, great. All right, so let's start off with this problem. Okay, so if I were to put in that t in our function, like I said, that means for every x you see, you're going to put a t next to it, basically. If you see a y, you're going to put a t next to it. Hopefully that makes sense. So I see an x up there. Guess what that's going to get? A nice t buddy. It's going to have t with that x. Got it? Okay, so I also see this y squared, so I'm going to put a t squared with that y squared. So that's something you should take note of. The power remains the same. Okay? So if the power remains the same, like I just said, then you're going to get that t to the fourth, x4 plus t4, y4. Okay. And if you see here, you can factor out a t to the 4 and then take that out of the square root. You get t squared. Right? And what we could see here is we could factor out that t squared down here. T squared y squared plus square root x4. That's a 4. Okay? Okay, great. Now, what should we do? Definitely notice that we could cancel this out, and we're left with a t down here. So okay. Okay, so what we have here is this. Basically what we have is, right, because this was our function that we started off with. This is f of x, y. So we got that, so check. It is a homogeneous function because there was no t's still left in there. We were able to factor them out, reduce them, and we got our function back. It would be non-homogeneous. Let's say we had like, just for instance, we had a t in there. Well, that's not an original function, so it's not going to be homogeneous. But luckily, I chose the right problem, and we got our function back. Great. So that is just part of the battle. That's half of the battle. Is it homogeneous? Yes. Okay. So now, what degree is our t at? Because in the definition it said f of x, y. We need to know what degree it's at. In the question it'll ask, is this a homogeneous function? Prove it, and at what degree is it at? Okay, so we just have to find the n degree. Well, what degree is this? T. Some might say the degree equals 1. If you say that the degree is equal to 1, well, you're wrong, because it has to be in this form, right? T to the n power. This is 1 over t to the n power, for instance. Well, if we want to get it into this form, it's going to be t to the negative 1. Ah, so our power, our degree, is equal to negative 1. So, is this equation homogeneous? Yes. What degree is it at? Negative 1. Because like I said, it has to be in this form. And it's not just because I said, it's probably because the person who invented these equations said. So, we have to follow. Make sense? That's how we're going to find whether it's homogeneous and what degree. Okay, so let's make this interesting and do a problem where it's not going to be homogeneous. So, spoiler alert, it's not going to be homogeneous. It's good to see what that looks like. Let's see, we have natural log. We have the natural log of x cubed, natural log of y cubed is equal to f of xy. Okay, great. So let's check if it's homogeneous. Well, I'm just going to reverse it. Just going to flip this around. And that's okay. Well, for every x, I'm going to put a t buddy, t cubed, right? And for every y, I'm going to put a t cubed. So, natural log of t cubed, x cubed, natural log of t cubed, y cubed. Great. Okay, so now what do we do? That's a good question. Well, based on our log rules, division, excuse me, division becomes subtraction. Division becomes subtraction. Okay, so how do we get rid of the t3, the t cubed? Well, the answer is you can't take out the t. So notice you can't take out the t. So therefore, this is not homogeneous. And there you go. So you see, this t is stuck in the argument and can't really go anywhere, can't factor it out, can't do anything. So we don't get our original f of x, y. It'd be an incorrect statement, a not true statement. So therefore, it's not homogeneous. Great. Perfect. Well, if they do ask you to prove that it's homogeneous or not, and to what degree it is, that's how you do it. Now going to solving homogeneous differential equations, because that's what we're trying to do, solve the equations. So solve. Well, two things to know. I put asterisks on them because they're pretty important. One thing to look for is, does it have terms like x over y or y over x? And you might see like sine of x over y. And to answer that question, yes, it does. And I'll show you what happens if it does. And another thing to know is the format. The format's pretty important. The format should be m dx plus n dy equal to 0. Okay? And if you've ever taken multivariable calculus, this may seem like you did that in that class, because when you're solving for a conservative vector field, you might do a similar computation like this. But we're to be solving for different things. Okay, so the method we're going to be using is a substitution method, basically. Okay, the substitution method, we're going to let v equal to x over y, or we could also say that x equals vy, and that's just manipulating the equation, basically multiplying y to both sides. And letting u equal to y over x. Or we could say y is equal to ux. And now the interesting part is, now if we make these substitutions, this is going to lead us, it may not always lead us, however, it may seem like it. It's just something I noticed. It leads us to use separable method. Okay? And if you can't remember these substitutions, because I'm sure your professor might say, solve this homogeneous equation, and you'll have to use these substitutions, and well, maybe I forgot them. Well, for me, I use the, I said this. I basically said why us, why ux. I don't know, it's just something that I remembered. Why us, why ux. And then that just let me remember this one. So if my way of remembering helped you, all power to you. Okay, so with that, let's solve a differential equation using this method. Let's get to the fun part. We've used enough words. Okay, so our problem is plus okay, so another way to figure out if it's homogeneous or not, well, one way was to plug in our t's into our function. Great, we could do that. Works every time. Or we can notice that all the degrees are the same. So for instance, this degree is 2. This degree is 1 and 1. Well, if I add those, I get 2. So that's 2 for this term right here. This is 2. Okay. So when the degrees are the same, that's usually going to indicate that, hey, I'm homogeneous. Also, now you're going to ask, which substitution do I use? I have to sneeze. Ah, that's embarrassing. So you're going to ask, what substitution do I use? This is going to be so which one of these am I going to use? Well, one question you should ask is, if this is attached to a simpler term, if your dy or your dx is attached to a simpler term, that's going to correspond to the substitution you're going to use. Okay? So this dx is attached to a y and an x. Well, that's pretty simple. However, compared to dy, which is attached to this x squared, you can see it might be a little more simpler. So because this dy is a simpler one, well, I'm going to use y is equal to ux. Okay? So let's use that substitution. So we're going to let y equal to ux. Okay, so if we take a derivative of that, we're going to get dy is equal to u dx plus x du. Great, great, great. So for our dy, we're going to plug this in, and for our y, we're going to plug in this. Okay? So we have y squared plus, we have u squared x squared plus u x squared dx plus x squared u dx plus x du equals 0. Okay, so if you notice, we took our dy and we substitute it with this. And we took our y's and we substituted it with our ux's, okay? Okay, great. Well, you could distribute this dx and you'll see things a little more clear as to what cancels out and what doesn't. So I guess we could do that. Okay. All right, so if we move this to the side, we're going to get all these dx's, right? We're going to get them all on one side. And we're also going to factor out an x squared. We could also factor out a u, can we? Yeah. So if we wanted, we were going to get so what I did was I combined these two first, right? And got 2ux. And I just factored out a dx actually. And you'll see why. And well, what's going to happen is it's going to cancel. And we're going to be left with u squared plus 2u dx is equal to negative x du. And then, here's where the separable method again comes in handy, is we want to get all our u's on one side and all our x's on one side. Like I said, this is the only time we want to get our x's in the same place. Okay, so, and that's basically how we remember the separable method, is by saying stuff like that. So if it helps you, all power to you. Then I'm going to divide. So I'm going to get negative 1. It's going to be 1 over x dx. It's going to be negative 1 over u squared plus 2u du. Okay. Now all my variables are on the same side as their differential. So now I'm going to integrate. Now usually professors don't like when you put the integral symbol. At least mine didn't really care for it. So I write it down so you know what's going on. You're going to take the integral, and then you're going to get the natural log of x plus c is equal to, and that's going to be essentially, because we're going to factor this out, this u. So we're going to get negative negative 1 over u times u plus 2, right? And this is where one of our techniques comes in handy. If you remember partial fractions being a way of integrating, we're going to have to use the partial fractions. So hopefully you remember how to do that. We're going to get right. Okay. And so hopefully you remember how to get the numbers. If we do the computation, our A is going to equal 1/2, and our B is going to be a negative 1/2. Okay, great. So now we're just going to put our A's where they go, our B's where they go. Okay. So now we have yeah. Okay. And then if I were to, because I still haven't integrated that, if I integrate that, I'm going to get okay. All right. Great. And let's not forget about our substitutions. So every time I see a u, I'm going to have to convert that back to y's and x's, because our equation is in terms of x and y initially, right? So we basically couldn't have it in terms of two other variables. So we're going to have the natural log of x plus c equal to negative 1/2 natural log of u is equal to y over x. So we can plug that in. U is equal to y over x. And then plus 1/2 u is equal to y over x. Oops, I forgot the natural log there. Natural log of y over x plus 2. And ta-da! There we go. And that's our answer. So that is basically solving homogeneous differential equations. Obviously there's going to be harder ones, but I'm glad that this one employed a partial fraction, because towards the end of differential equations course, you're going to find out in Laplace, you're going to be using partial fractions a lot. And Laplace uses partial fractions, I think, in most of its process of solving that equation. Laplace is one of the beautiful equations that you'll see in the end because, well, you can solve any order of differential equation, any higher order differential equation using IVP problems. Okay, so if you want to see a little more of these, we can. Since you like these so much, okay. It's a good one. It's also a good one. Let's do dy over dx y squared plus 1. Okay, so if you're wondering, well, is this homogeneous? Well, so going back, we want to make sure all the degrees are the same. And if all the degrees are the same, well, then it's going to be homogeneous, right? Well, unfortunately, you can't see right now that they're all the same, right? However, if we get them all under the same denominator, we're going to be able to see that they will be the same degree. So if we were to get them all in the same denominator, well, that's just going to be y cubed plus x cubed plus xy squared xy squared. Okay, so you might be saying, Mike, these are not the same degree. Well, then I would say, hey, these are the same degree because these are all degree 3. And how are they degree 3? Well, this one's obvious. Y cubed is degree 3. X cubed is degree 3. X is degree 1. And y is degree 2. So 1 plus 2 equals 3. So this term is going to be 3. Great. And then we have x with the degree 1 and y with degree 2. Add those together, you get degree 3. So all the degrees are the same, and that means that it is homogeneous. Great. So now we can continue to solve this using homogeneous method. Well, let's do it. Usually you see our method, or actually our format. Remember, our format was m dy plus n dx. Well, this isn't in that format, so we need to get it in that format, right? If we manipulate this, multiply everything out, we're going to get y cubed plus x cubed plus xy squared dx, all that times dx, minus xy squared dy is equal to 0. Great. Now we have it in that format, right? Now, which substitution do I use? Well, this is going to be clear because let's look at our dx. Wow, look at this term that it's attached to. You could say that this is a complex term to be attached to. Relative to that dy, which is attached to this itty-bitty term. Okay, so this will let us know that we're going to be using our y equals ux substitution again. Great. Okay, so, well, I'm going to take a derivative of that substitution, and I'm going to get dy is equal to u dx plus x du. Okay. Well, every time I see my y, go ahead and plug that in. Every time I see a dy, we'll plug that in. All right, so let's do it. Well, xu squared times x squared dx minus xu squared x squared u dx plus x du is equal to 0. Well, if I were to combine terms, make this a lot cleaner, that's going to be x4, so we can write that. Let's do that one. Well, let's just write out what we have. We have 3 cubed, that's going to be cubed, dx. If I multiply that over there, I'm going to get minus x4 u squared du equal to 0. That's plus. Okay. Hopefully you can see that. I'm sorry, this is minus. All right. Great, great. So now if we were to simplify, we're going to get okay. That's going to be equal to x to the 4 u squared du. Okay. And now our x cubes are going to reduce. That x is going to be simple x. Now we have 1 plus u squared dx equal to x u squared du. Okay, now this goes back to our separable method of solving differential equations, right? Now we have to put all our x's with our dx differential and our u's with our du differential, right? Okay, so let's do that. So when we do that, we're going to get dx over x being equal to u squared over 1 plus u squared du. Okay, okay. And now we're going to integrate, right? Because that's our separable method. And if you notice, well, this one's just going to be natural log of x plus c. However, this right here, that's going to be one of our integration by a glance. You can see that these degrees are equal. They're both 2. So what we're going to do is divide them, and that's going to make our integration a lot more simpler. Okay, so let's divide 1 plus u squared divided by u squared. Okay, so how many times can that go in? Only 1. All right, so if I do the computation, that's going to change, and then all I'm left with is a -1, right? So I'm left with a -1, and then this is going to equal 1 minus 1 over u plus u squared. Okay, and du. So now this becomes this. Okay, so let's just do that over here. So now I have the integral of dx over x is equal to integral of 1 minus 1 over 1 plus u squared du. My multivariable calculus professor always get mad if you didn't put those parentheses, and he's right, that's what it is, but he'd always joke with us that he would give us a 0 if we didn't put those parentheses. Okay, so now we do the integration. That's natural log of x plus c. Well, and if we remember the integration for that, well, that is simply tangent, inverse tan of u. Okay, so we want to remember that. I think that was in our calculus class. So now we get this natural log of x plus c is equal to, oh, we can't forget, we have to replace our u's, in this case, our u's. Okay, so our u is equal to y over x. So we're going to have y over x minus inverse tangent of y over x. And that is our answer. Great. And this is how you solve them homogeneously. I totally forgot to put an S. Homogeneous differential equations. Okay. And so that will conclude our homogeneous solving our differential equation using the homogeneous method. Next, we're going to be using the exact method to solve the differential equations.